Hey there, welcome back. Today we're tackling a question that's probably crossed your mind. If you've ever dreamt of building a wildly successful app,
Yeah.
what happens when your user base explodes to, say, 1 million users? Hmm. Maybe you're prepping for a tech interview,
Right.
or maybe you're actually building the next big thing.
Mm-hmm.
Either way, we're diving deep into the world of system design.
Okay.
Beyond the basics, designing for 1 million users.
It's a question that trips up a lot of people because, on the surface, building an app can seem pretty straightforward.
Yeah,
But once you factor in massive scale,
right.
things get much more interesting.
Totally. Imagine your app takes off and suddenly you have a flood of users signing up, connecting, posting updates.
Right.
What happens to your app then?
Well, if you built it the way most people start out,
Mm.
on a single server, you're probably going to start seeing problems.
Oh, no.
Latency, for one.
Okay.
You know that annoying delay between when you click something and when the app actually responds?
Yeah.
That's latency, and it gets worse as more users pile on.
And then there are the dreaded crashes.
Oh, yeah.
Not exactly a good look when you're trying to build a reputation.
Exactly. Plus, you might be stuck manually scaling your server, which is a headache.
Yeah.
And let's not forget about those unexpected bills from your cloud provider as your resource usage skyrockets.
Ouch.
You might even notice that your app performs differently depending on where your users are in the world.
Oh, so location matters too.
It can, yeah.
Okay, so we've got a problem. Our single server setup is buckling under the pressure of 1 million users.
Right.
What's our first instinct?
Many people think, okay, let's just give our server more muscle,
Okay.
more CPU, RAM, storage, basically what's called vertical scaling.
It sounds reasonable enough. Just supercharge that one server and call it a day, right?
Unfortunately, it's not that simple. Vertical scaling has its limits.
Okay.
You'll eventually hit a ceiling in terms of how much you can upgrade a single server.
I see.
And even if you could keep upgrading forever, you still have one major vulnerability. A single point of failure.
Oh, right.
If that one server goes down, your entire app goes down with it.
Makes sense.
And with 1 million users relying on your app, that's not an option.
So vertical scaling is like trying to solve traffic congestion by making a single lane wider. Eventually, you hit a limit and you're still stuck with a bottleneck.
That's a great analogy.
Thanks.
The real solution is to think horizontally. Instead of one superpowered server, imagine having multiple instances of your app running on separate servers, all working together.
So multiple servers.
Yep. This is called horizontal scaling.
Okay.
And it's how the big players handle millions, even billions of users.
So instead of one lane of traffic, we create multiple lanes, allowing users to flow smoothly even during peak hours. I'm starting to see the appeal of horizontal scaling. But how do we actually make this work in practice?
Yeah.
Do we just randomly send users to different servers?
That would be a bit like playing traffic roulette.
Uh-huh.
We need a system to manage all these servers and distribute traffic effectively.
I see.
Enter the load balancer.
Okay, I'm intrigued. What exactly does a load balancer do?
Think of it as the traffic cop of your system.
Okay.
It sits in front of your servers and directs incoming traffic to the least busy server.
So it knows which servers are free.
A simple way to do this is with a round-robin algorithm.
Okay.
The load balancer simply cycles through the list of servers, sending each new request to the next server in line.
Interesting.
This helps ensure that no single server gets overwhelmed.
So it's like a dealer dealing cards, making sure each server gets its fair share of the workload?
Exactly. But keep in mind that this is just one basic approach.
Okay.
There are much more sophisticated load balancing algorithms that take into account server load, traffic types, and other factors to optimize performance even further.
That's definitely something we can dive into another time.
Yeah.
For now, I'm pretty impressed with this traffic cop analogy.
Okay.
It's a clever way to visualize how traffic is managed across multiple servers.
And it's not just about traffic management.
Ooh.
The load balancer also acts as a security barrier.
Okay.
Since the client only ever interacts with the load balancer, it keeps your individual servers hidden from public view,
Smart.
reducing the risk of direct attacks.
That makes a lot of sense. So we've got our servers, our load balancer.
Right.
What about the data? Where does all that user information actually get stored?
That brings us to a critical decision. Choosing the right database.
Okay.
There are two main contenders.
Yeah.
Relational databases like Postgres and non-relational databases, often called NoSQL databases.
I've heard those terms before, but I'll admit they always make my head spin a little.
I understand.
Could you break them down for us in simple terms?
Of course.
Hmm.
Relational databases are like meticulously organized filing cabinets.
Okay.
They're excellent when you need strong consistency,
Nay.
meaning every user sees the same data at the same time.
Oh, I see.
Think bank transactions.
Yeah.
You don't want any discrepancies there.
Oh, sure.
They're also great for handling complex relationships between different types of data.
So for something like a social network where you have users, posts, comments, likes, all interconnected, a relational database would be a good choice.
It could be.
Okay.
But if you're really focused on scale and speed,
Right.
NoSQL databases might be a better fit.
Interesting.
Imagine a huge online store like Amazon
Yeah.
with millions of products and users.
Makes sense?
NoSQL databases are built to handle massive amounts of data
Okay.
and can be spread across multiple servers more easily than relational databases.
So easier to scale.
Yeah, the trade-off is that they might sacrifice some level of consistency. Different users might see slightly different versions of the data at different times.
So it's a trade-off between speed and consistency.
In a way, yes.
So it sounds like there's no one-size-fits-all answer when it comes to databases.
Exactly.
Okay.
The best choice depends on your specific application, your priorities,
Right.
and the type of data you're dealing with.
Okay, so let's say we've made our database decision.
Right.
We've got our servers, our load balancer, our database, all set for 1 million users, right?
Not quite. We still need to make sure our database itself can handle the load.
Oh.
It's easy to overlook.
Okay.
But the database can become a major bottleneck if we're not careful.
So even with all these fancy components in place, our database could still become the weak link in the chain?
It's possible.
That's a bit worrying. How do we avoid that?
The first step is to make sure your database is not tied to your application code.
Interesting.
Treat them as separate entities so you can scale them independently.
Okay.
Think of it this way. You wouldn't build your house directly on top of your plumbing system.
Good point.
You want the flexibility to work on each system separately.
That makes a lot of sense. So we've decoupled our database from our application code.
Yep.
What's next in this database scaling adventure?
Well, there are a couple of powerful techniques we can use to scale our database.
Okay.
Replication and sharding. Replication and sharding.
Replication and sharding.
Yeah.
Those sound a bit intimidating. Are we going to need a PhD in database science to understand this?
Don't worry. We can break it down into manageable chunks.
Okay, good.
First, let's talk about replication.
Okay.
Imagine you have a really important document, and you don't want to risk losing it.
What do you do?
Make copies, of course.
Right.
Store them in different places just in case something happens to the original.
Exactly. Replication is the same concept.
Okay.
But for databases, you create multiple copies of your database and spread them across different servers.
One common approach is the master-slave model.
Master-slave?
Yeah, you have one master database that handles all the right operations, like adding new user profiles or posts.
Okay.
Then you have multiple slave databases that are essentially synchronized copies of the master.
So the slaves are like backup singers, perfectly echoing the master's performance.
That's a great way to think about it.
Thanks.
They keep a mirror image of the data, which is incredibly useful for a few reasons. First, it helps us scale read operations.
How so?
Since all the slaves have the same data,
Right.
read requests, like loading user profiles,
Right.
can be distributed across them,
Makes sense.
taking the pressure off the master database.
Makes sense. It's like having multiple entrances to a popular concert venue.
Yeah,
Prevents everyone from crowding the main gate.
exactly. Second, it boosts performance.
Okay.
By separating read and write workloads, you're essentially creating dedicated lanes for different types of traffic,
I see.
which keeps everything running smoothly.
And third.
It provides that all-important redundancy.
Right.
If one of the slave databases goes down, the others can step in seamlessly,
Okay.
ensuring that your app remains online and accessible.
Yeah.
It's like having backup generators in case the power goes out.
You got it. Replication is all about building resilience and scalability into our database infrastructure.
Exactly.
Okay, replication check. Now, what about sharding? That one still sounds a bit mysterious.
Think of it this way. Imagine you have a massive library with millions of books.
Okay.
It would be overwhelming to try to find anything in a single giant room.
No, definitely. I'd get lost in there for days.
Exactly. Sharding is like organizing that library into different sections or rooms based on a specific criteria.
Okay.
It's all about dividing your data
Right.
across multiple tables or even separate databases.
So instead of having one gigantic table for all users,
Right.
we could have separate tables for users whose last names start with A, B, C, and so on.
That's the idea. The criteria you choose for dividing your data is called the shard key,
Shard key.
and a special algorithm determines how data is distributed across the different shards.
So if I'm searching for a user whose last name starts with K, the system knows exactly which shard to look in
Right.
based on that sharding algorithm.
Precisely. Now, there are different sharding techniques,
Okay.
and some are more sophisticated than others.
Okay.
The article mentions something called consistent hashing,
Okay.
which is a powerful way to distribute data evenly across shards, preventing any single server from becoming overloaded.
Consistent hashing.
Yep.
Sounds intriguing. Maybe that's a topic for another deep dive.
We could do that.
But for now, I think we've got a good grasp of the basics of sharding.
Yeah.
It's all about breaking down a massive data set into smaller, more manageable chunks,
Exactly.
making it easier to store, access, and manage.
Both replication and sharding play vital roles in scaling your database
Okay.
and ensuring that it can handle the demands of a million users.
This is all incredibly insightful. It feels like we've built a solid foundation for our system.
Good.
We've got our servers, our load balancer, a robust database strategy. But I'm starting to realize that even with all of this in place,
Yeah,
there's still room for optimization.
for sure.
It's like we've built a powerful engine,
Right.
but we haven't fine-tuned it yet.
You're absolutely right. There are several techniques we can use to squeeze even more performance out of our system.
Okay, like what?
And one of the most important is caching.
Caching, yes. The article mentioned that I'm all ears. What exactly is caching and how does it help us?
Think of caching as storing frequently accessed data in a readily accessible spot for quicker retrieval.
Okay.
It's like keeping your most used spices right next to the stove instead of digging through the back of the pantry every time you cook.
So instead of constantly fetching the same data from the main database,
Right.
which can be time-consuming,
Yeah,
we keep copies of that data in a faster, more accessible location.
that's it.
Okay.
Caching works by storing data in memory, which is much faster to access than disk storage. It's like having a mini library of your most read books
Yeah.
right on your bedside table.
I love those analogies. They make it so much easier to visualize these concepts.
Good.
But wouldn't it make sense to cache everything? That way, all data would be instantly accessible.
That would be ideal. But unfortunately, it's not practical.
Why not?
Memory is limited and expensive compared to disk storage.
Right.
Plus, it's volatile, meaning that if the server crashes, you lose all the cached data.
Oh, I see. So caching is a strategic game.
It is.
We have to choose wisely what to cache and what to leave in the main database.
Exactly. It's all about finding the right balance.
Okay.
There are different caching strategies and eviction policies,
Okay.
which determine what data gets cached and how long it stays there. It's a whole optimization game in itself.
Wow, caching is more nuanced than I initially thought. Definitely worthy of its own deep dive sometime. But for now, I'm curious about another concept the article mentioned, CDNs.
CDNs, or content delivery networks, are a game changer when it comes to delivering static content, like images, videos, and large files.
Okay.
They work by distributing copies of this content
Right.
across multiple servers located all over the world.
So instead of everyone downloading the same image from a single server, users get it from the server closest to them.
You got it.
Nice.
This significantly reduces latency
Okay.
and improves the user experience.
I see.
Imagine watching a video online and it keeps buffering because the server is halfway across the world.
Yeah, super annoying.
CDNs solve that problem, bringing the content closer to the user.
That makes perfect sense. And if I'm understanding correctly, CDNs are basically a form of caching,
Right.
but for static content.
You're sharp.
Thanks.
They leverage the same principles of speed and efficiency,
Makes sense.
ensuring that users get the content they need as quickly as possible.
Okay, so we've got caching for dynamic data and CDNs for static content.
Right.
It's like building a superhighway for information, making sure everything flows smoothly and efficiently.
Exactly.
But what about tasks that take a bit longer to process, things that can't be instantly cached or delivered via a CDN?
That's where message queues come into play.
Message queues?
Yeah, they offer a powerful way to handle tasks asynchronously,
Asynchronously.
meaning they can run in the background
Yeah, okay.
without blocking the main application flow.
So instead of making a user wait while a time-consuming task is completed,
Yep.
we can add that task to a queue and let it run behind the scenes.
Precisely. The article describes a model called publish-subscribe,
Publish, subscribe.
or a pub-sub,
Okay.
where different parts of the system can communicate with each other
Uh-huh.
through these queues.
I'm picturing it like a well-organized post office.
Okay.
One part of the system might publish a message saying, hey, I need this image resized,
Yeah.
and then another part of the system subscribes to that queue, picks up the message, and takes care of the resizing
Right.
without interrupting the main flow of traffic.
That's a great analogy. Message queues are all about delegating tasks
Cool.
and ensuring that everything runs smoothly without causing bottlenecks or delays.
It's like having a well-coordinated team where everyone knows their role and can work independently without stepping on each other's toes. This whole system is starting to look like a well-oiled machine.
And that's the goal of good system design, to create a system that's scalable, efficient, and can handle the demands of a growing user base.
We've covered a lot of ground here, from servers and load balancers to databases, caching CDNs and message queues. It's amazing to see how all these pieces fit together to create a system capable of handling 1 million users. But I'm curious what happens when those users are spread out all over the world. How do we ensure a smooth experience for everyone, regardless of location?
That's a great question, and one that the article addresses with a technique called geo-routing.
Geo-routing.
Yeah.
That sounds like something out of a sci-fi movie. Fill me in.
It's actually quite straightforward. Geo-routing automatically directs users to the nearest data center based on their IP address.
So if I'm browsing from Australia,
Mm-hmm.
I'll be connected to a server in Australia instead of one in Europe?
Exactly. It's all about minimizing latency and ensuring the fastest possible response times for users around the world.
That makes sense.
No.
But if we have data centers in different regions,
Yeah.
how do we make sure they all have the same information? We wouldn't want users in different locations seeing different versions of the data.
That's where data replication comes in again. We replicate the data across all our regions,
Oh, right.
ensuring consistency and fault tolerance.
Makes sense.
If one data center goes down, the others can seamlessly take over.
It's like having backup generators strategically placed around the city so no matter what happens, the lights stay on.
You got it. It's all about redundancy and resilience, making sure that our system can handle unexpected events and keep running smoothly for our users.
This is all incredibly impressive, but I have to admit my head is starting to spin a little.
I get it.
We've built this complex, distributed system with servers scattered across the globe, data flowing through different pipelines, tasks running asynchronously. How do we keep track of all of this? How do we even know if everything is working as it should be?
That's where logging and monitoring come in,
Okay,
and they're absolutely crucial,
I bet.
especially as our system grows in complexity.
Logging and monitoring, I mean, those sound pretty important.
They are. Yeah, think of logging and monitoring as the nervous system of our system.
Okay, interesting analogy.
Logging is all about recording events and actions that happen within our system,
Uh-huh.
creating a detailed history of what's going on.
I see.
Monitoring, on the other hand, gives us real-time insights into key metrics,
Like
server load, database performance, and user activity.
So logging is like a meticulous record keeper, diligently noting every event,
Yep.
while monitoring is like a team of doctors constantly checking the patient's vital signs.
That's a great way to put it.
Thanks.
And just like in healthcare, early detection is key. By monitoring these vital signs,
Uh-huh.
we can identify potential issues before they turn into major problems.
Specific tools for logging and monitoring, like
Right.
Grafana, Prometheus, and Datadog.
They help us visualize and analyze the massive amounts of data generated by our system,
Mm-hmm.
turning raw data into actionable insights.
So we can actually make sense of it all.
Exactly. It's like having a dashboard that shows us the heartbeat of our entire system.
This has been an incredible journey.
It has.
We've gone from a single server struggling to keep up
Right.
to a sophisticated distributed system designed to handle 1 million users.
1 million users.
And we've explored all the key components along the way.
We have.
It's amazing to see how all these pieces fit together. With all its intricate infrastructure working in perfect harmony, servers as the foundation,
Yeah.
the database as the central library, caching as the local market,
Yeah.
CDNs as the delivery network,
Right.
and message queues as the asynchronous task force.
It-
But before we wrap up, I want to make sure we leave our listeners with some actionable takeaways.
First, remember to scale horizontally. Don't try to cram everything onto one server.
Right.
Use multiple servers working together. Next, implement caching whenever possible.
Okay.
Store frequently accessed data in memory for lightning-fast retrieval. Number 3, choose your database wisely. We talked about relational and non-relational databases.
Right.
Think carefully about what best suits your application. Fourth, go stateless.
Stateless.
Don't tie user data to specific servers.
Okay.
Make it accessible from anywhere. Fifth, for static content like images and videos, always use a CDN. Sixth, utilize asynchronous processing through message queues whenever it makes sense. And finally, make sure you have proper logging and monitoring in place. This checklist is a great starting point for anyone building a system that needs to scale.
We hope you've learned something new and that you're feeling inspired to build the next generation of scalable, user-friendly applications.
Until next time, happy building, everyone.